All right. So let me start. Today we are going to discuss a few topics that cover general aspects of optimization, which I think just a good way to illustrate what you can do with convex optimization, other than trying to just solve a problem. Okay. So so far, the way we were thinking about the convex optimization is kind of like a game of trying to represent something as one of the preset optimization problems, right? We were doing it directly when we had minimization problems, say like minimize a convex function with respect to convex domain, okay? That was a typical game that we were using. Then I believe 2 lectures ago, we had another game when we were saying minimize the convex function subject to convex domain, where that holds in the worst case scenario with respect to a different variable. So it was robust optimization. Ultimately, it was still just a game of how to represent this problem as a convex problem. Okay. So 1 second. Right. So that was the game how to do this. Right. Now today what we are going to do is to do more analysis. And this would since it is analysis rather than problem solving exercise, natural questions that you probably have is how important is it, right? As in, we can survive without analyzing the problems as long as we can solve them. Thing is, though, that as long as you want to go at least a little bit beyond standard, you would have to encounter problems that cannot be directly solved, or the problems that are not obvious how to solve. And that is where analysis becomes important. So analysis is kind of like next step. When you deal with easy problems, you don't have to analyze anything. When you deal with more complicated problems, analysis is useful. So I'll just show you a little bit of it, and that I think will be sufficient to introduce you to the idea, right? So we're not going to do like a whole lot of it, just a little bit. All right. So let us begin. Okay, so let us start by considering our most familiar type of constraint, that is a linear inequality constraint. All right. This is where convex optimization started. You remember that if you had linear equality constraints only, you can still do it the problem as least squares. But as long as you have those linear inequalities, it is already LP, QP, or something, but is a convex optimization problem. You cannot solve it using algebraic tools per se. Okay. Now we can rewrite this inequality, and remember this is just a stack. This expression here, let me draw it. This expression here is just a stack of individual half planes, so individual linear inequalities. This is a vector expression. Vector on the left, vector on the right, and we assume that the inequality holds element-wise. Well, we can rewrite it as individual inequalities. Here, this is a typical half plane. This is a scalar inequality now, very transparent what it means. We can rewrite it in this way too. Those two are the same exact expressions. So again, half plane, like a single inequality that is taken from this stack of inequalities. Now, this is a hard constraint. What we mean by a hard constraint is that they have to hold. Like we don't have an option to violate any of them. That is just not allowed by any means. So they are hard constraints, okay? And hard constraints, the problem with them is how do you implement them when you do, let's say, gradient descent? If you're going to do gradient descent, how are you going to implement hard constraints? That is absolutely non-trivial. I mean, sure, there might be a way to implement them. It is just not clear how to. All right. All right. Instead, what we prefer is a soft constraint. Soft constraint is the idea that you put a constraint in your optimization function, in your cost function. So trying to violate constraint radically increases the cost. Radically, that by that I mean the cost grows so fast that in fact it would overpower all advantages or disadvantages associated with anything else. So as soon as you violate constraint, your cost starts to grow so fast that no other consideration would matter. So your gradient descent would completely be guided by violation of this constraint because of how fast the cost grows in this vicinity. All right, so that is the idea. Now here, what we can do is, for example, to turn this into a soft constraint, we can use a log barrier function. Okay? Log barrier function. And this, it has a form as presented here, equation number 4. Okay, log barrier. What is log barrier? Well, to understand how it works, we would have to think about logarithm. Who can tell me what logarithm does? Like, how does it behave near 0? Or let's say just, how does it behave near 0? Someone tell me. Just unmute and talk.
It goes to infinity.
Near 0, it goes to infinity. Plus infinity or minus infinity?
Logarithm minus infinity. Minus logarithm infinity.
So it goes towards minus infinity. All right. And even more correctly, you would say if you approach the 0 from the right, so it is a small positive number that approaches infinity, 0, then the answer is log approaches minus infinity. Whereas if it is approaches from the left, I think the correct answer is what? It's not defined, right? Logarithm of a negative number is not defined. Am I right? I mean, I'm I'm only partway asking for just for for engagement. Part it's like been a while since I looked at logarithm function, so there's a chance that I really don't know what's going on. So I think that's correct. So right, logarithm is not defined for negative numbers. We're talking. We write here a logarithm. We are of course talking about logarithm with the basis of exponent, but it would make absolutely no difference if you make it base of 10 in this particular case, because they behave similarly. This is not a differential equation, so like here we don't require the base to be natural, like it's to be natural logarithm. All right. So this guy approaches minus infinity when this expression approaches 0. All right. But right. Yeah, right. Everything is correct. Right. But this expression now, let us look at this expression here. This is the negative of this expression. So those two expressions are related. They're the same, but with a different sign. Okay. So this has to be always negative. This has to be always negative. So this has to be always positive in the domain. As long as we're sitting inside the domain, this is always positive, right? Okay. So this is always negative, this is always positive. Since it is positive, logarithm exists on the domain, okay? As long as this guy starts to approach the zero, so it gets closer and closer and closer towards the boundary of the domain. On the boundary of the domain, when ax equal to b, this is zero, okay? So as long as it becomes closer, this whole thing becomes bigger. It goes towards minus infinity, but we have this minus sign here. But let me use something. We have this minus sign here. This minus sign makes it from minus infinity to plus infinity. So the whole expression goes towards infinity. So in fact, this log barrier function starts to grow extremely rapidly when we approach a boundary of the domain. Inside the domain, though, it's actually growing very, very slowly. So the difference between log of, let's say, e squared and log of e is just 2, right? And the e squared and e are quite different. And if we have, let's say, log of 100 and log of 1,000, the difference is also like quite small. Quite small. All right. So what we'll find is that this function is largely flat inside the domain, but grows extremely rapidly at the edges of the domain. Okay. That is important point to keep in mind. Now, in order to use this function in convex optimization, we often add extended. There's the idea of a function extension. Function extension means that function is defined to be infinity everywhere where you don't have a naturally defined alternative value of the function. So, for example, logarithm is defined only from 0 to plus infinity, right? Or the domain is from 0 to plus infinity. Well, you can define it to be equal to minus infinity from minus infinity to 0, right? That is a way to, you can extend a logarithm function. So function extension is basically adding infinity as the value of the function outside of the domain. So just as an example, let's say you have a function on, this is a number line, okay? And domain of this function is represented by like two, let's say, values. Here is the domain of the function. This function is defined only on this domain. Let's say the function on this domain is a convex function, so it would look, now it will be very ugly what I'm going to draw because I'm using touchpad. Let's say this is what the function is on this domain. So what we do is we define the function to be equal to infinity everywhere else. So we say everywhere else the function is equal to infinity. So it is at infinity, okay? All right, and that would be extended function. If naturally it only has value on this part, everywhere else we'll say it is equal to infinity, and that is the extension. We can do the same with log, and then barrier function will be equal to infinity everywhere outside the domain. So that is that. All right. All right. This is convex function, by the way. This is convex function. Okay. That is quite interesting because I think this is not obvious. This is a convex function. Does everyone believe me that this function, the extended function, is convex? Does everyone believe me? Who doesn't believe me? Tell me. Unmute and talk. Who doesn't believe me? Everyone believes me that this is a convex function. Can someone prove me that it is a convex function? Okay, let me show you counter example that would maybe make you doubt. Let's say I define this function where everywhere outside the domain, the function is equal to, let's say, 10 billion. 10 billion. So very big number, not infinity, but you know, what is infinity? It's like, it's not a real number, so we have to pick something. Well, let's say 10 trillion, doesn't matter. Some very big number, somewhere, you know, in the stratosphere. How do we check that the function is convex? Well, we have to draw a line. We have to draw a line that connects the value, you know, the value of the function at one point, the function value of function at another point, and this whole line should be above the function. But here, clearly, it's not going to be above the function. Why? Well, because we have this rim here, right? Like this straight angle. It's impossible for the line to be on top of it, right? Like this line, which connects two values of the function, it should be on top of the graph. But there is no way, because it since the value here is lower than the value here, the function will have to have a slope that is negative, like a negative slope, right? But the slope here is positive, is zero. So here's zero slope, here's negative slope. So of course it has to go through the graph. So of course this part is going to be above it. So if we pick 10 trillion or whatever instead of infinity, we don't get a convex function. We get something, not a convex function. So how what can we do to make the function convex? Like, why is infinity convex? Like, what's going on? Can someone tell me? Or do you think now that maybe infinity is not convex function? Like this extended function where the value is at infinity, maybe you now think that it is no longer a convex function. What is your opinion?
If we go to infinity, the black line should be vertical line.
The flat line is not vertical. So the flat line is the green one, line here.
I mean the black
Black line. Yes,
yeah.
yes. Yeah. You got it exactly right. That is exactly the correct answer. So if we are at infinity, let me now use some different color. If we're at infinity, instead of this black line, we get this pink line, which is vertical indeed. Because the way we compute the slope of this line is we say changing the value of the function divided by the change of the argument of the function. Changing the value is infinite. Changing the argument is finite. You divide infinite by finite, you get infinite number, infinity. Okay, and then you do whatever you know, whichever way you want to compute your angle, like as a tangent, cosine, etc. Doesn't matter. The answer would be 90 degrees. You would get that the slope has to be 90 degrees. It's like vertical line. And the vertical line is never going to intersect anything because it is vertical. Trying to do this exercise from this point here is meaningless for infinity because that is like not a, I mean, you cannot do this exercise with infinite numbers. Like you cannot claim that a line of infinities is horizontal. Is just a meaningless thing to say, as far as I can understand. You know, it's like this mathematics of infinities is complicated, so I don't claim to know how you work with it. But you know, you have to be very careful if you're going to claim some property of infinite line to be horizontal. You have to basically explain what you mean by that. That was not going to be easy. So easy way to work with this whole thing is exactly as you argued, to claim that any line that connects here is going to be vertical. So great. Okay, all right. So the barrier function is indeed a convex function. Good. Now, next, let us just look at it a little bit. So if we replace our linear cost with a barrier function, what we achieve is the following. We remove a constraint, but we also modify the cost. Okay, so the cost is going to be different. And this means that optimal solution is also going to be different, because inside the domain, cost is modified, so optimal solution is shifted. A log has a very small influence on inside the domain, but still has an influence. You can multiply the log function, for example, by a small number, let's say 1/10,000. A log will then become even smaller inside the domain, but it will still be infinity at the edges of the domain. But the smaller log is, like more sensitive your finite steps have to be, because your finite steps can just in one step get outside of the domain if your gradients don't rise quickly enough. So there are trade-offs here. Often enough, what people do is also they multiply this expression here by a small number. So by multiplying this by a small number, you keep the infinity property at the edge. And you make essentially your log, instead of looking like this, log kind of naturally goes vertical, but then it slopes out. If you multiply this expression by a number, a small number, your log kind of looks more like vertical line and then instantly horizontal line. You don't have the slope that is very nice, like the slope. Instead, you have a vertical line, then horizontal. Okay, this is what you get from multiplying this by a small number. All right. So as I said, when this is a very small positive number, this is a very big negative number. Hence, you have this minus. All right. And barrier functions would not behave well outside of the domain, right? So you have to use like extended barrier function or do something else. So if you're going to use barrier functions by yourself, you have to consider this property. The barrier functions are not well behaved outside of the domain. Your solver, let's say CVX pi, uses barrier functions in order to solve your problems. So replacing all inequality constraints with barrier functions is one of the steps of methods such as interior point method. So you replace your inequalities with this. And then what you can do is, for example, treat your problem as locally being close to quadratic. So find, for example, a Taylor expansion of the cost up to the quadratic term. Then you can try to find your optimal gradient descent step, which depends on how fast you want to step down, which depends on how steep the gradient is. And that's it. So essentially, you can think about it this way. You have your problem. Is easy to compute gradient. Also, relatively easy to compute a Hessian. So second order term in the quadratic term in Taylor expansion. You can do that for all those functions, including the logarithms. And then you can choose how far you want to step in the direction of the gradient, so do gradient descent. And to do that, you analyze your Hessian, and you choose the step length with some heuristic, but also take into account the slope and the curvature. All right, Hessian is a curvature, gradient is a slope. Okay. Now, all of this is nice, and this is what the solver does. We're not going to discuss it beyond that here. Yeah, but importantly, it does this thing in order to solve your problem. So this is, and you can do it yourself if you're going to write your own solver. That is also needed. That's what you can do. If you're going to solve something with inequality constraints and you don't want them, you can always do this. Right? Notice that logarithm itself is like this whole function we just proved it is convex. Okay, this is a convex function, and this is good. So you can do it, but it is not part of any optimization scheme that we know. So this is not, for instance, SOCP, QP. It is not even SDP. This is a higher order optimization scheme. So this is not one of those standard optimizations. This is a more advanced yet optimization. Solvers usually don't allow you to do this inside the problem, as far as I know. You have some solvers that do. Some solvers do allow you to use this directly. All right. Now, let us see just one example. So here's a QP. The QP cost, QP constraints, inequality constraints, equality constraints. Okay. By the way, this shouldn't be brackets. It should be just multiplication. I don't know why we have brackets here. Okay. So we can approximate this problem by keeping the same cost. So the cost is the same, but we add to it what do you call it? Barrier function representation of our inequalities. So, those two are related. And we keep exactly the same equality constraints. Exactly the same equality constraints. So we transformed QP into what looks like unconstrained optimization. It's not, of course, but like we have constraints here. But remember linear algebra. So what we could do with these constraints is, for example, we could solve it for x. Again, this should be multiplication, not brackets. So we can solve it for x. And we can express x as C pseudo-inverse times D plus null space of C times new variable. We can substitute it in all of these expressions. What we'll get here is a new linear inequality. Fair enough. Here will be new quadratic function. And then it would be just unconstrained optimization, which you can try to solve by gradient descent, for example. All right. So this is how you can try to solve those problems. Do you have questions so far? Do you have questions? All right. Now let us move on. We can define something called analytic center of linear inequalities. Analytic center of linear inequalities is the minimum of a barrier function. Okay. Is the minimum of the barrier function. We can solve this as by solving this equation basically. So it is argmin over this guy from definition. So this is something that you can do. This is something that you can do. Some solver, I think if you do it in CVX Pi, I think it would allow you to do it. It will just choose a specific solver that is able to solve those types of problems. You can try. All right. At the analytic center of linear inequalities, the shape of contour lines. So what is a contour line? Let's first answer what is a contour line. So the contour line is the line with equal value of the cost function. So you remember maybe all those, what should I call it? Let's say this is a parabola. This is a parabola. So it would have contour lines, kind of like this. Let me try to use a different color. Contour lines would be something like this. I'll have to drag it around. Okay, so this is the control line where the parabola has equal value across the whole line. Yep. Or here's a big control line. Somewhere here. Okay. So contour lines is when the function has equal value across the line. Okay. Now, contour line for a function doesn't have to be like circular or anything like that. It's just something. It's just something. So the claim is that at the analytic center of linear inequalities, contour line has the shape of a quadratic function. So it is an ellipsoid. And the value of the quadratic matrix of this ellipsoid, so this, matrix of this quadratic form, you can say, or just like this Hessian, whatever you want to call it, that is like the Hessian of the Berry function would essentially define the shape of the contour line at the analytic center of inequalities. Okay. Okay. And here, the reason we say this thing is a small number, that is because epsilon defines basically the height of the control line, or in other words, it defines the size of the ellipsoid. So in the small vicinity of the analytical center, it's definitely true. But the further you extend this ellipsoid, the less true it is. So it's going to be a contour line as long as epsilon is small. If epsilon is not very small, then this is not a contour line. So that is the point. That is why we choose epsilon small, because contour line is going to be deformed. So let us just look at it visually. Let us just look at this visually. So here is an example. This is a domain. Okay. Everything that is colored is a domain. Okay. Now, blue is contour lines, true contour lines of the domain. Okay. So, for example, this is going to draw. This is a contour line. I'm going to just highlight it with a lot of arrows. So you notice it is not ellipsoidal. Like it more looks like a fat egg, if this is an appropriate analogy, deformed. But definitely not ellipsoid. You can see it is not ellipsoid. This is a true contour line. But if you look at the contour lines, let me use a different color. For example, this contour line, you can see it is even further away from being an ellipsoid. This is just something here. I mean, it's just something. And it's the closer the contour lines get to the edge, the more they resemble the actual shape of this geometric figure. So, for example, somewhere here, the contour lines would be just the same as the edge of this, polytope. Okay, so those are contour lines. But at the very center here, contour lines would be exactly the same as this ellipsoid, which is defined by finding quadratic component of your, tail expansion of your cost function of this Berry function. So the Hessian of the Berry function defines the shape of this contour. Okay. Now, all other, this green is the analytical center. Now, all other contours here, they represent the Hessian of the Berry function at this particular point. And the reason I draw them is because you can see how the Hessians become degenerate. As in, here the Hessian is just kind of becomes a line-like. Here it is a line-like, right? They all become degenerate. Notice the Hessians become degenerate, close to the edge of the domain. This makes sense. At the edge of the domain, this function does not behave as a how should I put it? As a function with curvature. More it behaves like a linear function. More it behaves like a linear function. You can say, oh, sorry, maybe that wasn't the best way to put it. What I'm trying to say, I guess, is that curvature in this direction. So let us just consider this direction, okay, like this direction, near the edge. So curvature in this direction will be extremely large. So we curve very fast upwards, okay? On the other hand, curvature in this direction is extremely low. We basically hardly curve. So the Hessian is going to be completely degenerate, okay? So it doesn't behave like a linear function. It basically behaves like a function which curves into one direction only, right? That's what I wanted to say. And this is a sign that you are next to the edge. Do you want to use it for your analysis? I mean, up to you. But if for example you want to analyze the shape of your barrier function, you want to see how does it behave. This represents an easy tool. So all you do is just study a second order approximation of your barrier function. And you would see how it behaves in each particular point. And for example, if your solution is near the edge, you can try to analyze the barrier function near this edge. But I also notice that you could, like all those Hessians could be found outside of the domain too. That is possible. How meaningful is it? Good question. But you could find them. But yeah. Also, importantly, if you want to analyze just how nicely your function behaves somewhere at the, let's say, like here, I'm trying to analyze how it behaves in the interior. It's also useful to look at those Hessians. If they are roughly circular, that is a good sign. That means that at the interior, at least, your barrier function does not influence much the gradients of your solution. You could also analyze the first order approximation and stuff like this, but at least you can see curvature that your Hessian adds is relatively small at the center. But let's say maybe your optimal solution is close to the edge. Of course, it's a different story there. So this is one of the instruments how you can analyze it. And this idea of analytical center of inequality is also useful for finding initial guess for your problem. Let's say you have a synthetic problem. Synthetic, I mean, it's not a real problem, a real engineering problem. It is more like a test case scenario. So you want to test case some method or whatever. And you want initial guess, which is for sure inside your what do you call it, domain, inside your domain. So one of the things you can do is use analytical center of inequalities as an initial point. Why am I talking about synthetic problem? Well, because in a real problem, it is easier to find optimal solutions than analytical center of inequalities. Optimal solution at least doesn't require you to solve a problem which is more general than SDP. So, finding analytical center of inequalities is actually a very hard problem. But sometimes you may want to do it just to get a valid initial point for your gradient descent. So if you want to, you don't care about the performance. What you care is a fair game where you always start with a valid initial condition. Then analytical center of inequality is an option. So and alternatively, maybe you want to even analyze to make sure that your initial point has some specific curvature properties. Again, use Hessian analysis. Well, this is just basically a set of ideas of how you can deal with your domain defined by inequalities. Questions? I have questions. Okay, no questions, then I will continue on. Now, second part. Let us consider a very general case optimization problem. Here we have a cost function. Here we have inequalities. Here we have equalities. Okay. We can find Lagrangian of this problem. Lagrangian is given by the original cost function plus your inequalities times lambda. Okay, times lambda plus your equalities times nu. So what's going on here? If you studied any optimization as part maybe of a calculus course or anything like that, you know that optimal of a constraint function is equal to the optimal of the original function plus Lagrangian multipliers times constraints. Okay, and that new function would have new variables, Lagrange multipliers, and you find optimality conditions for the Lagrangian, and this Lagrangian given as original cost plus Lagrange multipliers times constraints. This this new function, its derivative would be set to 0. Lagrangian coefficient, Lagrangian multipliers would be set to 0, etc. You will get not the Lagrangian coefficient, sorry, the constraints would be set to 0, etc. Basically, you would get the solution to the original problem using this this method. So this is the same idea, but now we have inequalities, and we also use Lagrangian multipliers there. Okay. Let me maybe just elaborate a little bit on what would happen if we didn't have this component. If we didn't have this component, and we didn't have this component, we have a constraint optimization here and unconstrained optimization here. How are they equivalent? Well, unconstrained optimization 9 can be solved by finding derivative of this function and setting it to 0. Derivative with respect to x would be, df dx plus something here, right, equal to 0. Okay. Fair enough. Now, derivative of this function with respect to nu, those variables, would be, this becomes 0. It doesn't depend on nu. Nu goes to 1 because it is a vector. So when you take derivative with respect to nu, you just basically get an identity matrix here. And this multiplied by identity matrix is equal to 0. So we recover basically this constraint by taking derivative of the Lagrangian with respect to nu. Okay, so we recover that this guy is equal to 0. But if this guy is equal to 0, then Lagrangian here would have this whole part equal to 0. Okay, so ultimately what we go back to is the original cost function satisfying the original constraints. Okay, satisfying the original constraints, and we'll find its its optimal value through the classical considerations, setting the derivative to 0. The same way we check optimality conditions, checking that there's a minimum, not a maximum. But since it is convex, it will only going to have minimum. We also have to check what happens at the edge of the domain, but that is a separate story. That's a separate story. Okay. So this is the situation here. This is the situation here. When we don't have inequalities. When we have inequalities, we have this more complicated stuff. But still, Lagrange unknown coefficients. So same stuff as in introduction to optimization or calculus. Okay, let's see how we use it. So sometimes, just important, sometimes we call lambda and nu as dual variables. Those are dual variables. Okay, dual variables. All right, let us see what we can do. So this Lagrange, okay, is associated with the Lagrange dual function. So Lagrange dual function, which is given by as g of lambda and nu, which is equal to infimum over x of the Lagrangian. So you have a Lagrangian, you minimize it over x for any particular value of nu and lambda, and you get a dual function, Lagrange dual function. So you can think about it this way. This guy, let me use, I guess, different color. This guy and this guy are the same. But this guy, in the red here, is this blue function, which is minimized with respect to x. So whichever value of lambda and nu you pick, it would still be, we pick such x that makes it smallest possible. Smallest possible, okay? So Lagrange dual function is always concave. We're not going to prove it, but that is a property. Lagrange dual function is always concave. If P star is the optimal value of the cost function of the original problem. So P star is the optimal value of, let me show, of the function f0, okay? Then this new function, let me give it back. This dual function g of lambda and nu gives us a lower bound on possible values of P star. So P star is again a optimal value of f0 on the domain. And then g of lambda and nu gives us a lower bound on it. So let's say the optimal value is something. But g of lambda and nu gives us, let's say it's equal to -3. So we evaluate this function. And gives us -3. It means that f of 0 cannot be less than -3. -3 is the lower bound. We cannot expect f of 0 to be less than -3. Let's say that this function for a different value of lambda and nu gives us 0. It means that the lower bound is 0 for f0. So f0 cannot be less than -3, but it also cannot be less than 0. Okay. Let's say that this value somewhere else for some other nu and lambda is 3. Then this function cannot be less than 3. So we have bigger and bigger lower bounds. But since it is concave, it has a maximum. So this function will have a maximum. And this maximum, by the way, we are only allowed to use lambda which are positive. We're not allowed to use negative lambdas. This has to do with the fact that f of x is purely negative. So lambda have to be purely positive. So in fact, since it is convex, we can find maximum, or concave, sorry, we can find maximum of this function. And this maximum is called optimal lower bound, and is denoted as G star. Okay. So we can find optimal lower bound. Let's say that the optimal lower bound is 10. That means that this guy cannot be less than 10. But it also means we cannot find any other lower bound. Like we can't find a lower bound that is larger than 10. 10 is as good a lower bound as we can get. Okay. Now, if P is the optimal value of the cost function of the original problem, and G star, P star, and G star is the optimal lower bound, then their difference is called duality gap. So let's say the optimal value of our function is, I'll write somewhere. Let's say the optimal value of our function is 15. That is P equal to 15. And let's say that the lower bound, optimal lower bound is 10. That means that duality gap is 5. Optimal lower bound cannot be bigger than the cost function, because optimal value of the cost function. That just wouldn't make sense by definition. So duality gap is always positive or 0. If duality gap is actually 0, then the problem is said to have strong duality. So we have strong duality then. If duality gap is 0, then we have strong duality. Okay. If optimal duality gap is greater than 0, so we cannot find duality gap that is equal to 0, and the problem is said to have weak duality. Okay. Then the problem has weak duality. So either it is 0 and we have a strong duality, or it is bigger than 0 and we have weak duality. If it is a strong duality, you can imagine we can just solve the problem of finding the largest possible lower bound, and that would be a solution. So we could solve the problem by finding the largest possible low bound. Okay. All right. Do you have any questions about this part? Okay. Now, let us consider a quadratic program again, same as before. Now we have a purely quadratic cost function and purely inequalities here. Let me denote them by a different color. So our Lagrangian is again original cost function, and our inequalities times lambda. Okay. Now let us minimize this Lagrangian with respect to x. To do this, we take the Lagrangian, okay, and we find its derivative with respect to 0. What we get here is 2x transpose h plus lambda transpose a. From this we get 1/2 x to be equal to 1/2 h inverse a transpose lambda. So we solve this as a normal unconstrained optimization problem, which it is. And from that, we recover x. Now, what we can do next is substitute this x back into here. So we substitute here, substitute here, and we substitute here. So we have 3 places where we substituted in the Lagrangian function. Okay. Essentially, we substitute here. Okay, let's do this substitution. So this is the value of x, and we substituted here. This is 1x. This is the other x. This is the last x. Okay, 3 places where we substitute x. When we get rid of this guy here, let me use a different color. We get rid of this guy here, and we recognize that we have a similar function. So again, I'll use different color. So this quadratic function is the same as this quadratic function. So we combine them, and this minus overpowers this, so we have minus 1/4. And this is the what do you call it? Lagrange dual function. So this is a Lagrange dual function. Now we want to find optimal lower bound. How do you find it? Well, we find it by solving this optimization, where we have our Lagrange dual function as a cost. And we remember that lambda are allowed to be positive, strictly positive. They can't be anything else, only strictly positive. Okay. Okay. Now, what is interesting here? So this just basically gives you optimal lower bound. Assuming that your problem has strong duality, solution to this problem will give you a solution to the original problem. Okay, that is assuming you have strong duality. QPs have strong duality. QPs have strong duality, as far as I remember. Other optimization problems don't always have strong duality, but as far as I remember, quadratic programs do have strong duality. You have to double check it. Don't just trust me. But as far as I remember, they do. Okay, now we can use such a concept as sensitivity, local sensitivity. Okay, what is local sensitivity? Well, local sensitivity is basically the values of lambda, optimal values of lambda for this problem. Okay, so when you do this problem, you'll find some optimal values of lambda. Okay, and those optimal values of lambda will tell you how much the constraints influence your the solution of your system. Okay, they will tell you how much your constraints influence the solution of your system. Okay, so ultimately, if the solution of your system lies inside the domain, constraints have zero influence on it. Okay, they have absolutely no influence on your solution. And if in this case, optimal value of lambda would be 0, should be 0. Okay, should be 0, unless I'm mistaken. So, yeah. On the other hand, yeah. By the way, yeah. Okay. I'm not sure if I'm still thinking about if QPs have strong duality. So please do double check it. If you're going to self-study, you can check Stephen Boyd's book. You will have a section on that. All right. Now so sensitivity tells you how much your optimal value, you can say, optimal value of your problem depends on your constraints. So if your solution does not lie on the boundary, it doesn't matter. Like it doesn't matter, your constraints have no influence on it. But if your solution does lie on the boundary, one of the constraints is going to have a very big influence on the solution. Okay, others are not. So sensitivity is kind of is given to you by this optimum value of lambdas. Okay, and you can study this, how the sensitivity works at any value of x, at any value of x. So you can plug any value of x to your Lagrangian, essentially, and then you can study how sensitive is your problem to this particular value of x. All right, so let me illustrate. So consider minimizing this cost here. Consider minimizing this cost. So the domain here is, let's say, this second quadrant. Okay, second quadrant. Positive x1, negative x2. So let us find sensitivity of this problem with respect to C. Okay. What do I mean with respect to C? Well, clearly, optimal value of this function would be C, right? X equal to C. This is the minimum value this function can attain. That will be 0, by the way. The optimal value of the cost function will be 0. The optimal value of x will be C. As long as C is inside this inequality. So as long as C is inside this polytope. This polytope, by the way, is not so much a polytope as a quadrant. It is the same as what we've written there. It's just a half space, 2 half spaces. And so in the intersection of 2 half spaces, it is a second quadrant. That's what it is. So as long as C lies in the second quadrant, we get optimal value is x equal to C. But if x does not lie in the second quadrant, C does not lie in the second quadrant, then we have a sensitivity with respect to the constraints. So, and we can analyze which constraint influence our solution how. So we can find our dual Lagrange function here. That's how it would look like. That it directly comes from the previous result. We just substitute a new h, which is basically identity here. That's what we get. Okay. And with that, we can actually plot sensitivity. So here, let me use it. This is our domain, second quadrant. So this is our domain. Everything that is in the second quadrant is our domain. Okay. Here is the position of possible positions of S. If S is in the second quadrant, sensitivity is 0. So our solution is not sensitive to constraints at all. But if the solution is anything, or the S is in any other quadrant, let's say the S is somewhere here, let's say. Well, those arrows represents values of lambda. So you can see here, arrows point upwards, and they are have a certain magnitude. So it means that in this case, it is this one of the constraints influences the solution. So the solution is sensitive to one of the constraints. Okay, and in particular, it is of course sensitive to. Let me draw it, I guess, here. 1 second. It is sensitive in particular to this constraint. So this is the constraint which is represented by the arrows pointing upwards. Okay. Let us analyze the behavior here. Well, here it is another constraint which does something, and it is this constraint. Let me use a different color. So to be this constraint that is influencing the sensitivity. The sign is flipped because the sign of the constraint was flipped. You remember one of the constraints is x positive, another constraint x negative. So the sign flips the sign here. But what it means basically is that in this quadrant, sensitivity is guided by this constraint. So this constraint is important. This isn't. Okay. So we have a whole quadrant where only one constraint is important, a whole quadrant where only another constraint is important. And here we have a whole other quadrant where both constraints are important. See? And you can even draw a line here. I guess it will be something like this, where across this line, both constraints are kind of equal. They have equal sensitivity. But the further you go into first quadrant, the more up this pink constraint is acting, the more you go to the blue quadrant, the more the blue constraint is active. So ultimately, you can use this sensitivity to analyze which constraint is being active at any given time. Of course, there are simpler ways to do it. You could, for example, just compute which constraint is violated. But also this, the length of those lambdas, etc., they give you kind of like the idea of how deeply the constraint is violated. And ultimately, since your solver usually gives you those Lagrange variables for free, you could try to use them in your analysis. For example, if your problem is being solved, you can try to see what dual constraints look like. Or if your problem returned no solution, you can try to, analyze how your constraints, which of the constraints are violated for like initial guess and so on and so forth. So this is yet another way to analyze your problem through your dual variables. And ultimately, solvers also do that. They often find that working with dual variables is somehow easier. One of the interesting parts about dual variables is the fact that in dual variables, you always have the problem with the concave cost and this very nice inequality. This is element-wise inequality that asks you to be positive. In literature, this would sometimes be called a, what do they call it, like R plus con, something like this, basically saying that you are only allowed to be positive. Or you can say it is a first quadrant con or something like this. This is a con, is a type of con. It's not a second order con, it's a different con. Semi-definite matrices is a semi-definite con. Second order con is what we call a con in high school. This is yet another type of con. Yeah, and this is just very nice. It's very simple. As long as you are happy enough to work with positive numbers only, this gives you a very nice optimization problem. But it doesn't guarantee you that solution to this problem will be the same as the solution to the other problem. So there is that. All right. So this is how we could do some analysis with two family of tools. Just a small recap. So first is barrier functions, which are actually used by solvers. And you can use barrier functions to find, for example, analytical center of inequalities, right? Analytical center of inequalities. And you can analyze contour lines of your function at the analytical center of inequalities using second order element of the Taylor expansion. And the second was Lagrangian, which gives rise to dual variables and Lagrange dual function that looks like this. And you can analyze, if you know something about duality gap problem, or if you can find it, you can reason about the solution to the optimal problem using Lagrange dual problem. And for something like QP, you can see it is actually quite easy to find a Lagrange dual function. Here is a Lagrange dual function. And you can try to solve it. And the solution will, for free, give you sensitivity analysis tools. So that is that. That is that. That is all I wanted to show you today. So if you have any questions. Right. If you don't have any questions, then I think on Thursday will be the last core lecture, I think. After that, we might have only bonus lectures. I will make sure, but I think that is the plan for now. And slowly but surely, we are coming close to the exam. So while we still have time for classes and so on, please, start thinking about reviewing the material, collecting your questions. I will, of course, provide Q&A sessions later so we can discuss it. But the faster we start, the better it will be. So, don't miss time. Try to go through material and see what exactly you don't understand, so we have time to review. All right, I think that is it. We'll see each other on Thursday. Goodbye.
Thank you, Professor. Goodbye.
Goodbye.
Thank you. Goodbye.